Okay, everyone, welcome to the Tutte Colloquia. So we are very happy today to have Alex Pothen. So Alex is a professor of computer science at Purdue University, and Alex works in scientific computing and combinatorial and graph algorithms. So Alex's research intersects quite a lot with the work of some of our colleagues in the department. And in particular, Alex is the first PhD student of our former colleague, Tom Coleman. And earlier this year, we were trying to make this talk around the time that we hoped that Tom could be with us. But sadly, we didn't manage to get it work, and Tom Coleman passed away. So, so we are happy that finally we get to this talk, and I'll give the stage to Alex to talk a little bit about Tom and also talk about his work on algorithms for matchings in big graphs.
Thank you, Jane. Thank you, first of all, for all the support that you provided over these past several weeks in organizing this talk, but also to Jochen for the invitation and all the colleagues in the combinatorics and optimization and computer science departments for your support and for your interest in this work. I have spent 2 years, 92 to 94, at Waterloo, visiting Alan George, and our family at the time, very young children, have very fond memories of Waterloo, and we spent quite a bit of time with Henry and his family as well. So we have some very strong connections to Waterloo, and I'm so sad that I can't be there in person to visit with you and to talk to you all in person. Also, Tom Coleman was my advisor at Cornell. I was his first PhD student. I had that privilege, and he introduced me to matching. Because when I was thinking about a PhD thesis, he told me to compute sparse bases for the null space of a matrix. And this is work that Tom and I did together. And then others like Steve Wavasis, for example, has worked on this problem. So let me begin by acknowledging his influence in my life and his support. And I do want to extend again my condolences to Yu Ying and all of the family and all of the Waterloo family, all his colleagues at Waterloo, on your great loss. And I hope that that the work that we continue to do will shine a light on the contributions that he has continued to make. So this summer we had a SIAM annual meeting, and we had a mini symposium in honor of Tom's work, and that video is now available. I think you should be able to contact either me or someone at Waterloo. Ewing, for example, would be able to tell you how you can be able to watch it. Perhaps you can make that available on your website. So thanks again, Tom. And I want to talk to you about approximation algorithms for matching. So a matching in a graph is simply a set of vertex disjoint edges. So at most one edge is incident on each vertex. So you can see that these colored edges form a matching because there's at most one edge incident on a vertex. Okay, and the black edges, these are the non-matching edges. So so on. And then of course one could ask to maximize or minimize number of objectives. Initially, the objective functions that we'll consider will just be linear. And so, for example, you might ask, I want to maximize the cardinality of the matching. That is, how many edges are in the matching? Or you could put weights on the edges, and then you could say, I want to maximize the sum of edge weights of matching edges. Or you could say, I want to put weights on the vertices, and then I want to maximize the sum of vertex weights, and so on. In fact, that problem is a problem that I'll talk to as soon as I finish this introduction. And then, of course, there are other problems. You could say, you can generalize this to B matching, where you say, there should be at most BV edges incident on a vertex V. So instead of BV being equal to 1, you could set BV equal to some other value, and that depends on V as well. And then there are complementary problems like edge cover and so on. So all of these problems we've looked at. And then, of course, one could look at nonlinear objectives. So instead of using linear objectives, you could use nonlinear objectives, and then you could ask for example, submodular objective functions and so on. So I'll sort of give you a flavor of some of the work that we have done in this area. And perhaps it's appropriate to begin by saying, what has been done in terms of exact algorithms, right? And these are actually classical problems in combinatorial optimization and computer science. And they have been studied by many of your colleagues who have associations with the University of Waterloo, and particularly the Combinatorics and Optimization Department. So Tutte and Edmonds and Cook, and I understand Professor Cook is in the audience, Cunningham and Polyblank, and then many others. Okay, if I've forgotten to name somebody, please forgive me, but those are the names that I could think of right away. And then, polynomial time algorithms are for these problems are available, and they were available from the earlier work, but also, more efficient algorithms have been designed by folks like Hopcroft and Karp, and Mikhaili and Vazirani, Gaba and Tarjan, and several others. Okay, and indeed, efficient implementations of these algorithms are available in tools like Lida or Lemon, which is freely available, and Matchbox, which is a code that we have developed. However, these algorithms are impractical for big graphs. So if you talk about graphs with billions of edges or more, they don't terminate in hundreds of hours. And we've seen several examples of this. So that motivates us to think about approximation algorithms. So now we're no longer able to solve the problems exactly. So we scale back our objective and we say, well, we just want an approximate solution, but we want to prove something about how good the solution is. We don't want a heuristic solution that this gives us no bound, but in fact, we want to prove some bound. So these algorithms often run in time that is linear in the size of the graph. So they're blazingly fast. They can be implemented efficiently. Many of them can be implemented efficiently on parallel machines. And then, one doesn't really need to get the approximation ratio very high. Something like half or 2/3 or 2/3 minus epsilon approximation algorithms. In practice, these are actually fairly close to optimal, as I'll show you in some of the results I show you. And in terms of combinatorics, it relies on matroids and their relaxations, short augmenting paths, ideas of randomization, primal dual formulations, making proposals as in stable matching, and so on. And we'll see a few of these in this talk. So we have, in fact, surveyed the work on approximation algorithms for matching and edge covers. This is work that's been done in the last 20 years or so. And the development of parallel algorithms for these problems, and and the applications, number of applications. We did this in an article. This is a 90-page article in Actor Numerica in 2019. And in this talk, what I will do is to highlight just a few of these algorithms. So I won't go into great detail about any particular problem or algorithm, but I just kind of want to give you a quick overview of 3 of these problems and then an application. I hope you will interrupt me and ask questions anytime during the talk. If there are, if something that I say is not clear, or you want to comment on anything I've said, so please feel free. Okay, so in terms of approximation, so first of all, I want to say something about what do I mean by approximation algorithms, and I want to make a distinction between approximation algorithms and heuristic algorithms, right? So we've seen the problems with exact algorithms. Approximation algorithms, we've seen the advantages that they can be faster, they could be concurrent, and the solutions might be nearly optimal, so you're not giving up much in terms of quality and so on. But heuristic algorithms are algorithms where there's no provable approximation guarantee. So in this case, maybe the problem is inapproximable. That is, you can sometimes prove that no good approximation algorithm is possible. So for example, for coloring and so on, you can prove such bounds, right? So having set the stage and provided some motivation, I want to talk about maximum vertex weighted matching, which is a problem that has not been well studied at all. So it's quite surprising, and perhaps maybe not so surprising, but there are reasons why one should study this problem more carefully than has been done before. So now think about the numbers at the vertices of this graph, not as vertex labels, but as weights. Okay, so now what I want to do is I want to find a matching in the graph, and I want to maximize the sum of the weights at the endpoints of the matching edges. So for example, this edge will give me a weight of 13. This will give me a weight of 9. This will give me a weight of 5, and so on. So, so in fact, this is a maximum vertex weighted matching in this very simple graph. And this is what we want to do. And when we're faced with a problem of this kind, one of the first things to ask, which is not what I did, so I mean, don't do as I did, but do as I say. So is to ask, what is the underlying combinatorial structure? And there's a beautiful combinatorial structure, which I call the Forgotten Metroid, because in fact, in some classic books on Metroid theory, you'll never see if you look at the index, you'll never see a matching Metroid mentioned. But this indeed goes back to a long time ago to Jack Edmonds and Ray Fulkerson in a paper in 1965, where the Metroid, as in any other Metroid, you have two sets. You have a ground set. Here, the ground set is a set of vertices, and then you have a collection of independent sets, and a subset of vertices is independent if those vertices are contained among the endpoints of some matching, right? So that's a Metroid. You can show, in fact, it's connected, it's related to transversal Metroids and other Metroids and so on. So there is this beautiful Metroid, and that immediately says that if you want to solve this problem exactly, you have an algorithm. It's a Metroid greedy algorithm that will compute a maximum vertex weighted match. And here is an algorithm. So you match the vertices in non-increasing order of weight, so decreasing order of weights, let's say, by simply searching for certain paths that we'll call augmenting paths. You'll see what they are, and if you don't know anything about matching in the next slide. We can search for these paths in the graph, but you cannot put a restriction on the length. So you have to, these paths could get arbitrarily large. They could be as large as n-1, say, for example, and that might happen, but you cannot restrict that length. You have to do this work. And then you match these vertices in order. So, if it can be added to the matching, then you add it. If not, you reject it. And then you go to the next vertex and so on. So it's a Metroid greedy algorithm, but with this augmenting path searches that are quite expensive. And that then runs in order nm time, but n is the number of vertices and m is the number of edges. And again, the problem is this is fine as it stands, but it's too slow for big graphs. So, but immediately this Metroid structure helps us because it says that the Metroid structure leads to this algorithm that says you can restrict your search path length. So there's augmenting path lengths to 1 or 3, and then you can get a half approximation or a 2/3 approximation algorithm. And these algorithms run in near linear time. So these are blazingly fast algorithms. But unfortunately, there's still a weakness with this approach, and that's this algorithm is not concurrent. It's not parallel. So if you want to solve a really, really large problem by throwing tens of thousands of processors of the problem by using the memory on those things and having these machines communicate, well, then you can't really do this effectively because you have to process the vertices in decreasing order of weight. So you have to process in that order, so you really can't exploit any parallelism at all. So we're going to come up with a better algorithm. And for this better algorithm, I need some concepts. So I need the concept of an augmenting path, for example, which is standard in matching theory. But let's see what it is. So an alternating path is a path that alternates with non-matching, matching, and non-matching edges, right? So that's an alternating path. And then an augmenting path is a path like this, which begins with unmatched vertex and ends with an unmatched vertex. So by simply flipping, the matched edge to an unmatched edge and taking the non-matching edges to matching edges, you can increase the cardinality of the matching. So this is an augmenting path. And this is, in fact, all classic algorithms for finding maximum cardinality or maximum weight matchings are based on these ideas. So this idea is not new at all, right? So we're just using the standard notion of an augmenting path in this context. But there's one more. So I need, in fact, in this context, I need the context of the concept of a weight increasing path. So this is now, again, an alternating path, right? Non-matching, matching, non-matching, matching. But now it's an even length path. So there are 4 edges. But this matching edge has weight 10. This matching edge has weight 3. So by flipping, again, non-matching, matching to non-matching, and non-matching to matching, I've now increased the weight because I've given up a weight of 3, but I've gained a weight of 10. So I've increased the weight of the matching. But I've not increased the cardinality in this case, but I've increased the the weight. And so these two concepts are what we need. We need a concept of an augmenting path and a weight increasing path. And in fact, we can generalize. We can say, this we call an augmentation. An augmentation is either an augmenting path or a weight increasing path with exactly k non-matching edges. So for example, here's one non-matching edge. So this is a one augmentation. And here is possibly a weight increasing path with one non-matching edge. So that's one augmentation as well. And similarly, these are two augmentations because there are two non-matching edges. So this is again an augmenting path. This is a weight increasing path. And those are all the 1 and 2 augmentations that you need to worry about for vertex weighted matching. So, so this concept now gives us an algorithm. So this leads us to this algorithm that says, so this notion of a k augmentation, right? So it's exactly k non-matching edges. So the theorem says if a matching does not admit a k augmentation or an L augmentation for 1 less than or equal to L less than or equal to k, then it is a 1 minus 1 over k plus 1 approximation to a maximum vertex weighted matching. Okay, so what this says is that now you don't have to look for augmenting paths or augmentations that are arbitrarily long. You can just restrict yourself to very short augmentations, and then you can get an approximation algorithm to the problem. So if you put k equal to 1, for example, you're just picking edges, then you get a half approximation algorithm. And if you pick k equal to 2, I've shown you the 1 and 2 augmentations in this previous slide. So if you look for these things and get rid of them in the algorithm, in the matching, then you have a 2/3 approximation algorithm. Okay, and that's a really nice result. And it's also, in fact, true for maximum cardinality matching and maximum edge-weighted matchings as well. The only thing we have to be careful about, we have to define, what a k augmentation is in a particular context. So it turns out that in the case of an edge-weighted matching, the k augmentation becomes, a little more, a few more sets of, paths or cycles or edges or things like that you have to look at. So this work was done with a former student of mine, Ahmed Al-Hirs, and he's finished his PhD last year, and now he's a professor in Saudi Arabia at King Fahd University in Durham. Okay, so that's the approximation algorithm that we have, and that immediately leads to this algorithm that says, okay, just go look for short L augmentations, and if you find one, go ahead and augment. If you don't find one, then just go to if you go to the next higher value of L, and if you can't find that, okay, you're done, because if there's no k augmentation, then the theorem guarantees you a 1 minus 1 over k plus 1 approximation algorithm. And indeed, in practice, you really want to initialize with the cardinality matching. So you want to that will make sure that the number of augmentations that you need to do is a lot smaller. But even if you don't do it, I mean, the runtime complexities and so on that we can prove actually work in that context. Okay, so now we've seen two algorithms. One is based on the Metroid duty algorithm and restricting ourselves to short paths. And then here's this other algorithm that's based on k augmentations that actually looks for weight increasing paths as well, not just augmenting paths. And here are some results. So I just wanted to compare, so this is the Metroid algorithm with short augmentations. These are the algorithms that I just talked about. So 2/3 augmentation and half augmentation by looking for 2 augmentations or 1 augmentations and so on. And then these are algorithms that they're not designed for vertex weighted matching, but edge weighted matching, but they can be used in this context. So I want, we'll look at a couple of these two algorithms we'll look at a little later in the talk. But for now, you just want to say these are competing algorithms that can solve the problem. Okay, and here this is a 1 minus epsilon approximation algorithm, and you choose epsilon to be 1/3. So you get a 2/3 approximation, so you can compare the quality with these things. And if you, in fact, make epsilon smaller, you don't get better quality. I mean, in practice, you don't. So unfortunately, the way to measure the quality of these algorithms is to measure what we call a gap to optimality, because it's so good. So what we do is we take the weight of the approximation matching, divide by the weight of the maximum matching. So this quantity is less than 1, and you subtract from 1. And then to make it a percent, you multiply 100, right? So you can see how close to optimal they are. So the worst of these is like a 1% off. So it's 99% or close to that, 98.75 or something like that, right? But most of them, so this one's 3% off, sorry. But most of them are actually, 0.2, 0.3, 0.76 and so on. And in fact, this 2/3 augmentation algorithm that I just talked about is simply 0.08% off. That is, so it's actually giving you 99.9 something of the weight that you would get for an optimal problem. Now, I said that these are on tail graphs which are fairly large, but where the exact algorithm terminates. There are lots of problems where the exact algorithm does not terminate. And in those cases, of course, we have no idea about the quality other than to say it's at least 2/3 approximate. We have this approximation guarantee, so we know that the worst case guarantee is true, and therefore we at least know that as a fact. And then in terms of run times, you can see what we do is we take the exact algorithm and take the time for it and divide by the time of the approximation algorithm. So here, smaller the better. Here, the larger the better, right? So the larger the number, the better, because it's so much faster than the exact algorithm. And you can see this 1 - epsilon approximation algorithm is a fairly complicated algorithm. It's a fairly sophisticated algorithm, and it's actually slower than the exact algorithm. Of course, these are sort of preliminary implementations. I'm sure that people could work on it and improve things a little bit and so on. But definitely these sort of ordering seem to be reasonable. So the 2/3 - epsilon is about the same time, and the pseudo algorithm half approximate is about 43 times faster. And then the 2/3 greedy, this is the Metroid, the short greedy algorithm derived from the Metroid algorithm, is about 20 times faster. And this augmentation algorithm that I just told you is 40 times faster. And if you're just willing to live with half augmentation and give up a little bit of the quality, then it's about 100 times faster on these particular problems. Okay. All right. So that and these algorithms are parallel as well. So not all of them, but for example, this is not parallel, but this is. And this is, and so on. So you can implement them on parallel machines. And I'm not going to show you parallel results for this problem because I'm going to show you parallel results for the edge-weighted matching problem. So I'll pass on that. But these algorithms can be implemented in parallel, and they do bring up interesting issues of when you augment from different processors, these augmenting paths could run into each other. So you have to make sure that there's no deadlock and live lock and so on. So there are things that you have to be careful about. But again, that's not something that I'm going to take the time to talk about today. So this is a good time to ask me a question if you had anything at all about the vertex weighted matching or any comments that you had before I move on to the next topic. I'll pause for a few seconds. Okay, don't hear one, so I'll move to the second topic, which is maximum edge-weighted matching and B matching. In fact, I'll mostly talk about B matching, as you will see. So in B matching, we're given a function BV that maps a vertex to a natural number. So in this case, for example, take BV equal to 2 identically, although it doesn't have to be, right? So it's a function of V, so you can choose it to depend on V, right? So it's a maximum weighted B matching. It's a subset of edges so that at most B edges are incident on the vertex, on a vertex B. So I hope you can see the colors. This is green. This is, for example, black. This is black and so on. Maybe the colors are not so well contrasted, but in any case, this happens to be a 2 matching for this graph. And you'll notice there's only one green edge incident on these 2 vertices. But unfortunately, you can't make it any bigger because if you choose this black edge, you'll violate the B constraints that there can be only 2 green edges on this vertex. So there'll be 3, and that's not a B matching. And similarly, you can choose this edge and so on. So in fact, this is a maximal B matching in this case. Okay, so these problems also have been studied somewhat. And again, the question to ask is, what's the underlying combinatorial structure? And the underlying combinatorial structure, is not that of a not of a matroid, but it's a relaxation of a matroid. And here we have, again, a ground set where the ground set is now the set of edges. And then you have a collection of independent subsets of edges. And what makes an edge, a set of edges independent? Well, it happens to be the set of edges in a matching, in a B matching, okay, in some B matching. So that makes the collection of independent sets. And now we can ask the following question. We have 2 B matchings, M1 and M2. M2 is the bigger one that contains M1. And there's an edge that's outside M2. So it's E minus M2. And you add E to M1, and you get a B matching. But suppose you add E to M2, you don't get a B matching. So there's a problem. Then what can you do? Well, you can do this. You can take M2, add E, and subtract off some set Y, and get a B matching. And the property here is that y does not have to be any bigger than 2. You have to remove at most 2 edges to do that. Okay, and that's very easy to see from the matching, from B matching perspective. If the edge, so M1 is a B matching, so it satisfies the B constraints. M2 is a B matching, so it satisfies the B constraints. So if I add this new edge E to M2, what could happen is that I might violate the B constraint on U and violate the B constraint on B. That's the worst I can do. And so I just remove one matching edge incident on U and one matching edge incident on B from M2, and that's my set Y, and Y is now less than or equal to 2. So if Y is less than or equal to K, it's a K extendable system. In this case, Y is less than or equal to 2, so it's a 2 extendable system. And then there's a beautiful theorem of Julien Mestre from about, I believe, 2006 or something like that, that says that if you have a K extendable system, then what we will call the greedy algorithm here. This is not the Metroid greedy algorithm, but this greedy algorithm is a 1 over K approximation to the optimal solution. So the greedy algorithm for B matching is half approximate. And what is this greedy algorithm? Well, this greedy algorithm doesn't, again, have to look at augmenting paths of arbitrary lengths. In fact, it just looks for edges. So it looks for augmenting paths of length 1. That's it. So so I'll call this the length restricted greedy algorithm. And what does it do? It just sorts the edges in decreasing order of weights, and then you add an edge to the matching. So you process an edge for possible inclusion in the matching. If you can add that edge and satisfy the B constraints, then you can add it. Otherwise, you toss it and then you start with the next edge. So this is a very simple greedy algorithm that doesn't even have to look for any paths of any kind and so on. And that is half approximate. So that's really getting a half approximation algorithm here is not much of a problem. Okay, but there's one problem with this algorithm, namely it again has no concurrency, because you do have to sort the edges and put them in decreasing order of weights. And so you have to, so again, you might have 1,000 processors, but only one processor which is working on the current heaviest edge can make a decision before anybody else can proceed. So you really can't use parallelism in any way here. So there's a whole slew of algorithms that have been developed for these problems in the last 20 years or so. So the greedy algorithm probably is a folk algorithm that goes back even before Avis's time. But an important development was from Robert Price in Germany in 1999, who said, you don't actually have to sort the edges and put them in decreasing order of weights and process them in that global ordering. It is enough to look at the local neighborhood. So it's enough to look at the neighborhood of an edge, and so on. So here's a neighborhood of this edge. So the neighborhood of this edge is all the edges that share an endpoint, with it. And so as long as you are heaviest in this neighborhood, that's good enough. Okay, so that's a local greedy algorithm. And furthermore, he showed that in fact it's a half approximation. So you can lose nothing in the approximation property. And now it's concurrent. So now you can make it concurrent. And so so this led to a lot of developments. And a lot of other people then started developing, there's a whole slew of half approximation algorithms that have been developed. I'll talk about one. I'll talk about Tutte algorithm due to Frederick Mann and Mahantesh Halapanawar, and then our generalization to the bsuite problem, and also talk about this 2 augmentation algorithm, which gives you a better approximation ratio. It gives you 2/3 minus epsilon, and it's due to Seth Petit and Peter Sanders. Seth is at the University of Michigan, and Peter is Karlsruhe in Germany. And then there is this algorithm due to Seth and his student Ran Duan, who is now at Tsinghua, which is a 1 minus epsilon approximation algorithm that actually is a fairly sophisticated algorithm that has to use scaling and so on. Some of these algorithms are parallel, but not all, right? So again, I want to talk about this 2/3 minus epsilon approximation algorithm, and that uses this notion of 2 augmentation, very similar to the 2 augmentation that we just talked about. So this is a randomized algorithm. And what we do is we choose a vertex U at random, and then we have to find a best 1 or 2 augmentation. We've seen this notion in the vertex weighted matching case, but now we have an augmentation that's centered at U, and then we have to augment the current matching with it. Okay, and I'll explain what this augmentation centered at a particular vertex is in the next slide. But for now, we just say, okay, we have to do a particular kind of augmentation, and then we have to repeat it a certain number of times. If you repeat it n log 1 over epsilon times, then you can prove in expectation, because this is a randomized algorithm, in expectation, you get 2/3 minus epsilon approximation. Okay, so So what's an augmentation centered at a vertex? So here's U. So let me use a pen so I can mark this. So here's U, and I'm centering it. So I call this an arm. So it's an arm, it's simply a path STU, where ST is a matching edge, and TU is a non-matching edge. And so this is an arm centered at the vertex U. And what you want to do is you want to find an arm that actually gives you the maximum increase in weight, right? This is what you want to do. And then what you do is you look at the vertex V if it is matched to U. And then again, you look for an arm here. So you look at an arm here centered at V. And then you have to make sure that these two are non-intersecting. And then using both arms, you find the highest gain to augmentation centered at U or V. Okay, and this is what you have to do, to find this to augmentation, and then you repeat it a certain number of times, and just do this randomly, and you get a 2/3 minus epsilon approximation algorithm expectation. So a beautiful algorithm, and it can be de-randomized, but the de-randomized algorithm is not so simple, so it's a little more complicated. But this works very well in practice. So I want to now talk about the pseudo algorithm, which is again a half approximation algorithm. So it's not 2/3 minus epsilon; it's slightly less than that. But again, has very good performance. And I bring it up because it is quite well connected to the stable matching problem, that many of you probably have read in the textbook literature that dates back to Gale and Shapley and McVitie and Wilson, for which Shapley won the Nobel Prize in economics, Nobel Memorial Prize in economics in, I believe, 2012. So here, these algorithms, in fact, are intimately related. So in fact, you can show there is a mapping, a pseudo algorithm with edge-weighted matching to the stable matching problem. So you can generate, given an edge-weighted matching problem, you can generate a stable matching problem, and then you can show that two algorithms actually correspond. So here, vertices make proposals, and a vertex can propose to match to its neighbor, and they have to do it in a particular order. They have to make sure that they propose in decreasing order of weights, and proposals could be either accepted or, as in the stable matching case, it could be rejected. Here, it's actually not rejected, it's annulled, okay? And each vertex simply keeps track of the best proposal that it receives at any point in time. So, so here's how proposals work. So U proposes to V if it can beat the best offer that V currently has. Remember that V stores the best offer that it has at any point in time. And then U proposes to V, and then if it can beat it, and then it simply goes ahead and annuls any previous offer that V has. So V doesn't have to act to reject it. You can just go ahead and annul the proposal. Okay. And when is a matching? When does an edge get matching in this proposal-based scheme? Well, when two endpoints propose to each other. So two endpoints of an edge propose to each other, then in fact, they are currently the best locally, and so they can match. And you can show that the expected number of proposals is not very large. So if you have a complete n by n bipartite graph, then the expected number of proposals is order n log n if the edge weights are chosen uniformly at random. Of course, you can choose edge weights to be bad so that it actually is order n squared. But again, in practice, if the weights are chosen, if the weights come from some reasonable distribution, then you don't see that sort of worst case behavior. But it could be really bad potentially. Okay. Now, what's really interesting about this algorithm is it computes exactly the same matching that the greedy algorithm finds. So in spite of the fact that we have made the algorithm so much more concurrent by simply having vertices propose to each other, and any vertex can propose, but they have to propose to their neighbors in a particular order, then the concurrency is a great deal more. But as long as weights are, ties in weights are broken consistently in different algorithms, then it finds exactly the same solution that the greedy algorithm finds, and therefore it's actually half approximation. So this is just a visualization of this. V1 is about to make a proposal. V3 has already proposed to V2, and so the V2 has stored it the best proposal that it has currently, the best weight it has now. V1 says I can beat it, and so V1 simply just deletes, announces this proposal and says okay, and then writes 3 there. So it becomes a it proposes to that. In this situation, the distribution of weights is reversed. And so now V1 looks and says, okay, I can beat 3. So there's no point in my making a proposal there. I might as well propose to my next heaviest neighbor that I can make a proposal to. And so anyway, the algorithm is fairly simple to state and fairly simple to understand. All I want to say is, okay, this algorithm has been implemented very efficiently. And if you can generalize this to B matching, there is a bsuite algorithm. And this is work, again, that one of my students, Arif Khan, did some years ago. And what we want to show is that this algorithm is highly concurrent, right? Because vertices can, it's a vertex-centric algorithm. Vertices can propose any vertex can propose at any given time. So there's plenty of work to do. It's just that you have to follow a particular discipline in the way in which you propose to your neighbors and so on. So, this is a distributed memory machine with 16,000 processors. And these are three problems, synthetic problems, actually, so that you can generate large graphs. So these graphs have billions of edges, 2 billion edges or so, and so on. And you can see that, as we increase the number of processors from 256 to 16,000 and so on, the algorithm scales very, very nicely. So this is running time that's increasing linearly, with the number of processors. So, simple algorithm, although it has some deep connections to stable matching problem, but it can be implemented very efficiently. So, again, this is a good time to stop and ask me a question. I'm chugging along, but I'm happy to take a minute or two and answer any questions or comments that you have. Okay. I'll move on to submodular matching. So now the objective function is no longer linear, it's nonlinear, right? And again, I suspect that most of you in the CNO department know about submodular functions and submodular optimization, so on. But in any case, let me just quickly bring everybody up to speed. So think about this problem where you have some circles and every circle covers a certain area in the plane. And what you have to do is you want to choose a certain number of circles to cover the maximum amount of area that you can cover. Okay. So here's a situation where you have three. So these we have already chosen to cover. So these filled blue circles have been chosen already. And now we choose this red edge, and the marginal gain is the additional area that's covered by the red set. Okay. And here the situation is similar, except that these three sets are included, but there's another fourth set, blue set, that we have chosen. So in this case, again, we choose the red set, and the marginal area covered by the red set is smaller. Okay, so this is a notion of diminishing returns. So if you have a set and a superset, and then you want to add a new set to this collection of sets, then the coverage, is smaller, for the superset rather than the small set. If this is true, then the function is submodular. So coverage functions typically tend to be submodular. So mathematically, a little more formally, we're given a set X, a ground set, and we have two subsets of X. We have a function f defined on all subsets of X. So it's submodular if you take an element E that belongs to X but not in T, and then you add it to S. S is the smallest set, and this difference here, Fs union S plus E minus F of S, is greater than Ft plus E minus F of T. So T is the largest set. Okay, so this is a submodular function, and again, they have really nice properties of continuous functions. So there's connections to concavity, convexity, and so on. But for now, let's just talk about what are called monotone submodular functions. So F is monotone if you have a superset, the function for the superset is smaller than or equal to the function for the subset. Right? So, and what this condition simply says is that instead of taking this E X minus T, you can just take any E in X, and then this definition will still go through. So, the application problem that we look at actually has a monotone submodular function. So this is why we restrict ourselves to this problem, and the algorithms tend to be simpler for monotone submodular functions. Okay, so now we can talk about a submodular B matching. So the objective function is now submodular. So again, we have a graph. We have these B constraints, upper bounds on the degree of each vertex. Delta V is the set of edges incident on any vertex V. And we create the 0, 1 variables X of V to indicate if an edge is in the matching or not. So if it's in the matching, the value is 1. And then, this is just a B matching constraints, right? So this is an integer linear program. You take E that's incident on a vertex V, and then you sum up the XV values, and it should be less than or equal to BV for every D in B, and then XC is constraint is 0, 1. So it's an integer linear program. And of course, if this function were linear, then we would have an integer linear program. But in this case, this function is not linear because I've taken this objective function and I put a square root on it so that this function is now nonlinear. And so this is one example of a submodular B-matching function or a B-matching problem. Okay, so this is one example of a submodular objective function for submodular B-matching. Okay, and so now this problem is no longer a polynomial time. So this problem is NP-hard. Okay, it's intractable. But it's known from work of Nemhauser and Wolsey from 1978 that the greedy algorithm, again, there is kind of a special greedy algorithm, not the Metroid greedy algorithm, but this restricted greedy algorithm, will in fact do a submodular optimization and give you an approximate solution. So in each iteration, what we do is we choose a feasible edge. Feasible just means that the B constraints are not violated when we're choosing that edge and putting it in the matching. So we choose an edge with a maximum marginal gain, and it's known to compute a 1/3 approximate B matching. Okay, so it's 1/3 approximate, actually, any submodular optimization for monotone submodular optimization, but in this case, it's true for B matching. And we can actually do better than this algorithm. And again, this is known from 1978 because most of the gains, the marginal gains, don't need to be updated. You can do a lazy update. You can update it just when you need it. And so this is the marginal gain of an edge is monotonically decreasing or non-increasing in the algorithm. So we can avoid most updates of gains. We only need to do it when you need it. And here's how we do it. So this is called the lazy greedy algorithm, and this is due to Minot. Again, dates back to 78. So what we do is we maintain a priority queue of marginal gains of the edges. And in each iteration, we pop the current top E and update its marginal gain. So we have that value correctly. And then what we do is we compare its gain with the next element in the queue and see if it beats that. Okay, so the gain for this next element may not be correct, but it doesn't matter. If you update it, it'll decrease anyway. So if the current top can actually beat it, then in fact it is currently the one of largest marginal gain. So you could simply go ahead and add it to the matching. Otherwise, you have to update the gain of the element E and push it into the queue and then continue. So that's a simple lazy greedy algorithm. It's actually a fairly well-known technique from, as I said, 78. And then what we do is we marry it with this notion of a locally dominant matching from Robert Price. So I said, here's an edge with a particular marginal gain. Look at all of its neighboring edges. If its marginal gain beats the marginal gains of all these edges, then in fact, you could go ahead and put this into the matching. And so that's this notion of a local algorithm that says, I'm just locally dominant in terms of marginal gain. And therefore, I can just go ahead and add that to the matching and then continue. So again, what this does is this makes the algorithm highly concurrent. You can now don't have to wait for the greedy algorithm or the lazy greedy algorithm and do things in a particular order. But in fact, you can just look in your local, in local subgraphs and make decisions as to whether an edge is in the matching or not, and so on. So again, you can use a large, high degree of concurrency here. So this is a local lazy greedy algorithm that combines both these ideas. And no surprise that it's 1/3 approximate for submodular B matching. And again, the algorithm is fairly simple. It's an iterative algorithm with 2 steps. In the update step, we simply find the vertex with for each. So find an edge with the highest marginal gain, and then we'll say V points to U. And then once you do this after the update, then you look at the matching step. If you have vertex that points to U and U also pointing to V, then again you have a locally dominant edge. So you can go ahead and throw that into the matching, and you continue this way. So that's the algorithm. And the algorithm again is linear in the number of edges. It's linear in the maximum value of B, and in logarithmic in the maximum degree. So that's the algorithm, and it works very well in practice. And of course, this can be made parallel as well. So unlike the greedy algorithm or the lazy greedy algorithm, which permits a certain amount of parallelism, this gives you a much better level of parallelism. Okay, and again, there are a whole bunch of algorithms here going back to Nemhauser and Wolsey, Minot, and so on. Some of these algorithms are practical. Many of them are quite impractical. But here's our algorithm, and it's 1/3, and that's the runtime. And unlike all these algorithms, this algorithm is concurrent. You can actually implement it in parallel, which is what we did. Because this problem came to us from a chemistry setting, and that's why we solve the problem. So let me conclude in about the few minutes that I have. Let me talk about quantum chemistry on supercomputers, right? So here's a load balancing problem that came to us. So there's this code called NWChemX, which is a quantum chemistry sort of density functional theory computation software library from one of the DOE labs. It scales to a very large number of processors, okay? And what they had to do was, they have this big computation called the Fock matrix computation. Each element in this matrix is essentially a multidimensional integral. And then you want to take blocks of these elements that need to be computed, and you want to assign these blocks to processors in such a way as to balance the amount of work and balance the amount of communication. So what we balance the load essentially by using an implicit formulation by using the submodular objective function. And then the B-matching problem, the B-matching constraints come from balancing the number of messages to be sent in a message passing library called MPI. Okay, and here's a visualization of what it does. So this is the amount of work, and this is what the default, and this is the number of processors. And this is sort of the default load balancing scheme that they use currently. And you can see the work is around 150,000 or so. And you can see the jagged nature, that it's not really balanced well. But here's the submodular B-matching based load balancing scheme. And you can see it's quite a bit less than 150,000, and it seems to be very well balanced. And of course, this is just a visual way of convincing you. You can look at these numbers and convince yourself. I won't take the time to look at those numbers right now, but this is the proof of the pudding. So we take this load balancing approach, integrate it with this NWChemX software, and run it on 14,000 processors. And we don't run it, they run it. I mean, we just give them the load balancing code, right? And you can see this is what their default scheme is, and it takes about 100 seconds or so with about 14,000 processors, and we take about 25 seconds. So we get a factor of 4 improvement just by balancing the load and balancing the communication, carefully. And in fact, this is for just one iteration. There are about 50 iterations that are needed to do this computation for this protein called ubiquitin. And so you can see this is on Summit, the second most powerful computer in the top 500 list. So, saving 4 times the amount of, instead of taking 24 hours, taking 6 hours, gives 18 hours for the computer to do more useful work on somebody else's problem. So this is what, we've been able to do. And that's been very, very satisfying. There are a number of other applications. Internet advertising is, in fact, the problem where the largest matching problems in terms of size and money. There's this notion of adaptive anonymity, the graph construction for semi-supervised classification, network alignment, and so on. But since my time is getting close, let me conclude very quickly. So we've designed several approximation algorithms for degree constraint subgraph problems. The design paradigms that we have seen include greedy and short augmentations, proposal making, randomization. I didn't talk about primal dual, but that would come up if I talk about BH color. These algorithms with constant approximation ratios yield nearly optimal solutions fast on both serial and parallel machines. And some of these algorithms can be implemented efficiently on parallel machines. Let me just point to you, my students here. Ahmed was the one who did vertex weighted matching. He's now a faculty member in King Fahd University in Saudi Arabia. Arif Khan is, again, a former student who worked with me on B matching and adaptive anonymity problems. And he is now a staff scientist at Pacific Northwest National Lab. Fardoz is a current student at Purdue. He's the one who worked on BH cover and submodular matching, and he's just about ready to defend his thesis next in a couple of weeks. And then 2 long-term collaborators, Fredrik Mana at the University of Bergen in Norway, who worked on the Tutte algorithm, not with me, actually independently with Mantesh, but who helped me write the approximation algorithm survey that I'll point you to. And then Mahantesh Alapanawar, a former PhD student from many years ago, who's also at Pacific Northwest National Lab, who worked on the Tutte algorithm. And we're working on this Exagraph project, which is designing algorithms for computers that can do 10 to the 18 operations per second, so extreme scale computers. So this is where a lot of our funding has come from. So I'll point you to the papers that the work that I talked about. We have a software library called Matchbox, and then here's Acta Numerica survey article if you want to know more about this topic. So I'm just about 45 minutes. So let me just take 1 more minute to say that all of this work came through in the context of community building. The community is a community in Siam called Applied and Computational Discrete Algorithms, ACDA, and this community was just started about 2 years or so ago. I had the privilege of leading the creation and the birthing of this community. And the very first conference on ACDA 21 was held this summer in July, and it's a hybrid conference. So discrete math conferences tend to be you just give talks. Computer science conferences tend to be you write papers and have them reviewed, and then you have those papers presented. We have a mixture of both. So because we want to kind of build a community that involves both groups of people. And so, and the first conference was held, and I think there were about 20 papers or so published in the proceedings, so you can take a look. But again, this might be a community that might be of interest to some of you. And if you are, then this is an activity group in SciEm, and you might think about joining this group. So thank you for your time and attention, and I'll be happy to answer any questions or comments that you have.
Well, thank you, Alex, for the very interesting talk. So now it's question time. Let's see if there is a question from people in the audience.
Yes, I have a question. So thank you for the talk, Alex. I was just wondering, have you ever used random walks to find augmenting path? So I'm asking because there are these papers by Goel and Karpalov that find so they give sublinear time matching algorithms in certain cases, and they use these nice ideas with random walks to find short augmenting path. Have you ever seen this?
No, I know of the work, yeah, but I don't think it has been considered in this context. So the Tutte approximation algorithm that I pointed to you does use randomization, but it uses randomization in the following sense, right? So it needs to, the analysis just says find an augmentation short arm that is at least, that is at least good on the average. But in fact, in practice, people find the best, so on. So definitely, random walks have also been used in the context of another problem, which is, finding matchings fast in regular graphs, and so on. Yeah, but those ideas have not been explored here, and potentially, and definitely, Karpalov and so on, their work would fit in the context of online algorithms and so on. So yeah, there's plenty of work to be done here in terms of real practical algorithms in terms of how they behave and how they might do. So no, I have not thought about them, but definitely worth thinking about.
Thanks.
Thank you, Ethan. So other questions?
Hi, this is Steve. Interesting talk. Thanks, Alex. Maybe I missed it, but is there any difference between the bipartite and the non-bipartite case?
For some problems, yes, and other problems, no. So I'll tell you the story of vertex weighted matching, right? So I gave that as a PhD thesis problem to Mahantesh around the 2005-2006 timeframe. And he and a former postdoc of mine, a former PhD student and a postdoc of mine, solved that problem for bipartite graphs, right? So, and we didn't know how to solve it for non-bipartite problems at that point in time. So the non-bipartite solution came with Ahmed Al-Hers, who worked with me in the last few years on that problem. But now that we understand the problem a lot better, in fact, this notion of k-augmentation simplifies the way you think about it, and it just makes life a lot easier. So, for example, to show that the short Metroid greedy algorithm, if you restrict that to short lengths, that it actually gives you an optimal solution, those proofs are actually quite complicated. And I, maybe we were just not smart enough, I don't know, but in any case, once you have the k-augmentation idea, the proofs are just very simple. They're very short and they come across very, very naturally. But having said that, in practice, though, there's a difference. So in practice, for example, I didn't talk about bipartite vertex weighted matching, but it turns out you can use, again, a theorem called the Dalmage-Mendelson theorem. Some of you might know about Dalmage and Mendelson were both Canadian graph theorists, actually, from the 60s. And they have this beautiful theorem that says, if you have, a bipartite graph and you have two matchings, then it's possible to take the two matchings and construct a new matching, a third matching, such that, you know, all the vertices matched by the first matching from one vertex set, and all the vertices matched by the second matching in the second vertex set, you know, are matched in this new matching. And so that gives you a really nice way to solve bipartite vertex-weighted matching problems by just looking at one-side weighted matching problems. So in practice, those tend to be a little faster as well. So yeah, I mean, so depending on the problem, you know, this notion of whether you use bipartite, whether you exploit the structure of a bipartite graph or not makes a difference. But because we are looking at short augmenting paths, thankfully, you know, the odd cycles don't give us much of a problem. So we don't have the problems of having to construct blossoms and shrink them recursively and so on, because those make the algorithm, that should make the algorithms very complicated and would make it very difficult to implement them in parallel in practice. So yeah, so it's a mixed bag. Some problems, it makes sense to look at the vertex, the bipartite structure of the problem, because you can actually design better algorithms, you know, that are more efficient. But for other problems, it doesn't seem to make a difference.
Okay, thanks. That's interesting.
Yeah. So yeah. Anyway, so.
Thank you, Steve. Are there other questions? Okay. I have a question, but I think it's probably better for me to ask before the recording, because it's it might be a little silly. So let's unmute ourselves and thank Alex for such a great talk.
Thank you very much. Thank you all. Yeah.
So I'm going to stop the recording now, and people can stay and discuss a bit more or talk about the other stuff.